Alright, now that we've had time for everybody to log in and we've checked to make sure that the audio and the video is working okay, let's get into today's webinar. So welcome everyone, thank you for being on time. This is going to be the next in our series of GCSE Chemistry revision webinars for 2019. This one is going to be on chemical change and various types of chemical reactions. So let's have a quick look at the topics that we're going to be covering here. So these are the topics for today's webinar. We're going to be covering these not necessarily in this order, more in the order in which you voted for them. Now, in keeping with the format and structure of the previous ones in this series, we're going to begin for the first hour by going through the topics in the order in which they received votes from you. Following that, we'll have a 5-minute break. And then in the next 55 minutes, we'll either continue to go through the topic, or we will go through the exam questions that you received in your exam style questions pack for this webinar. Again, many of you voted already on the resources page for this event as to which of these questions you found most challenging. So if you should choose for me to go into exam questions in the second hour, we will be going through the exam questions in the order in which they received votes. After that, we'll have another 5-minute break, and during that 5-minute break, you will all be able to vote as to whether or not you'd like me to continue for an extra 30 minutes, either on the topics for this webinar or on the exam style questions, or whether you'd like me to go into the Q&A segment. So to remind you again, if any questions arise that you'd like me to answer during the course of the first 2 hours, please do type those questions into the Q&A panel on your interface, and that will allow other students in your student group to upvote the questions that they feel are the most relevant or the ones that they'd like me to answer. Now, in that last 30 minutes, I'm going to be going through those questions in the order in which they receive votes. Okay, so let's get into chemical change then. Now, the first thing that you all, or the one aspect of chemical change that received the most votes was the idea of redox reactions. So I'm going to begin with that. So redox reactions are chemical reactions in which oxidation and reduction are occurring at the same time. Now, in chemistry, there are 3 different definitions of oxidation and reduction which appear in different contexts. So we can say that oxidation either occurs when oxygen atoms combine with the atoms of another element, forming an oxide. It can also be when hydrogen atoms are lost from an element or a compound, or when an atom or chemical group loses electrons. And so we have 3 different ways in which, or 3 different types of chemical change which can be classified as oxidation. So an example of an oxidation reaction is the addition of oxygen to magnesium atoms to form magnesium oxide. So this is a chemical change that we encountered in the last webinar on calculations in chemistry. But we'll be revisiting this a bit later on in this one. So that's oxidation. So reduction similarly can occur in 3 ways, and these are the opposite processes to the ones being described here. So reduction can happen when oxygen is removed from another element or compound within a molecule or within a substance. It can also be when hydrogen is added to or combines with a different element or compound, or when an atom or chemical group gains electrons. So there are various mnemonics that you can use to memorize the definitions of oxidation and reduction. One of them is LEO-REG. Loss of electrons is oxidation, and reduction is the electron gain. Another one is OIL-RIG. Oxidation is loss, reduction is gain. But you can use any one of these. Now, these 2 mnemonics refer specifically to the loss or gain of electrons or hydrogen. So loss of electrons is oxidation, but loss of hydrogen is also oxidation. So loss of electrons or loss of hydrogen is oxidation. Reduction can be classified as either the gain of electrons or the gain of hydrogen. So you can use either of these 2 mnemonics to keep in mind the definitions of oxidation and reduction as they apply to electrons or hydrogen atoms. But oxidation or reduction as applied to oxygen atoms is the opposite. So there are many chemical reactions in everyday life that involve substances reacting with oxygen to form oxides. So as we saw, these would be defined as oxidation reactions. So for example, living organisms when they carry out the process of aerobic respiration, they're carrying out essentially an oxidation process. The overall equation for aerobic respiration involves the addition of oxygen, or the chemical reaction of oxygen with glucose. And so overall, it is an oxidation process. Now, similarly, when fuels containing carbon and hydrogen or hydrocarbon fuels are burned in excess oxygen, then again, this is an example of an oxidation reaction. Now, oxidation and reduction reactions in ordinary chemical processes always happen simultaneously. When one substance is oxidized, for example, one substance combining with oxygen, another one is always reduced or loses oxygen. And so the term redox is a hybrid of the terms reduction and oxidation. It means a reaction in which oxidation and reduction are occurring at the same time. So an example would be, for example, lead oxide reacting with carbon to form lead and carbon monoxide. In this equation, lead oxide loses oxygen atoms and therefore is described as becoming reduced, and at the same time, carbon receives oxygen or bonds with oxygen and therefore can be described as being oxidized. So the lead oxide is the substance that provides the carbon with oxygen, and so it is said to be the oxidizing agent. The carbon, on the other hand, is the substance that removes the oxygen from another species, and so this is said to be the reducing agent. So the substance that is oxidized is described as being the reducing agent, and the substance that is reduced is described as being an oxidizing agent. So when magnesium burns in air, we get the following reaction. And so for a balanced symbol equation, we can write this. So when the magnesium reacts with oxygen, each magnesium atom loses 2 electrons and is oxidized to form a magnesium ion, Mg2+. Now, as there are 2 magnesium atoms, 4 electrons in total are lost, and each of the 2 oxygen atoms gains 2 electrons and is therefore reduced to form an oxide ion, O2-. So as the magnesium is oxidized, it loses electrons, and because the oxygen is reduced, because it gains electrons, the oxygen is said to be reduced. And so redox reactions can be thought in terms of the loss or gain of electrons. So in fact, oxygen does not have to be present for a redox reaction to occur. Once oxidation and reduction reactions are explained in terms of the loss or gain of electrons, it can be seen that there are a lot of reactions that can be classified as redox reactions. So oxidation and reduction reactions involve the transfer of electrons. One substance gains electrons while the other substance loses them. Oxygen doesn't have to be present for this to happen. So here's an example. When iron reacts with copper sulfate solution, the atoms of the iron each lose 2 electrons to become iron ions. Copper ions are displaced from the sulfate and gain 2 electrons to become copper atoms. So here would be the equation that's describing this process. And so we're going to be talking about displacement reactions in a little bit more detail when we start to talk about the reactivity series shortly. But you'll see here that we have ions being produced from atoms or atoms being produced from ions. Now this goes back to the definitions of the term atom and ion that we covered in the last webinars of this GCSE Chemistry webinar series. So in this case, the iron atoms, and again remember that atoms are electrically neutral because they contain an equal number of electrons and protons, the iron atoms have lost electrons, they've been oxidized and therefore have formed iron ions. So we go from uncharged electrically neutral iron atoms to dipositive iron ions. Now conversely, the copper ions in the copper sulfate solution have gained electrons and have become electrically neutral copper atoms. So the reactivity series of metals can be used to determine whether one metal will displace another metal from a compound. Now, a more reactive metal can displace a less reactive metal from a compound. So here's an example. If we place an iron nail in a beaker of copper sulfate solution, the iron will displace copper from the solution to form iron sulfate. And again, this is because iron is higher up in the reactivity series than copper. The iron nail becomes coated with a thin layer of copper, and the blue copper sulfate solution becomes the pale green colour characteristic of iron sulfate solution. So we're going to be looking at the reactivity series in a little bit more detail shortly, but to illustrate, we have this iron nail being placed into blue copper sulfate solution. Now, when we put this in, we find that over a period of time, as the reaction proceeds on the surface of the iron nail, we have the copper building up on the outer surface of the iron nail. So when the iron reacts with copper sulfate solution, the iron atoms will lose each 2 electrons, and these are therefore oxidized. And once they're oxidized and form ions, they go into solution. Now conversely, the copper ions floating around in solution on the surface of the iron nail will gain electrons. Each one will get gaining 2 electrons from the iron atoms, and thereby forming solid copper atoms in the solid state, which then accumulates over the surface of the iron nail. So once again, here is the equation to show what's happening in this reaction. Now, on the other hand, if we take a strip of copper metal and place it in a solution of magnesium sulfate, in this case, because copper is lower in the reactivity series than magnesium, we have no reaction occurring. So we can use the relative reactivities of different metals in the reactivity series to predict whether or not a displacement reaction will occur. So here we can see a table showing the metallic elements and compounds of those metallic elements, sulfates, and here we can see whether or not a reaction between the metal and a metal compound, a metal sulfate, will result in the metal displacing the metal from the compound. And we can see here that magnesium is higher in the reactivity series than aluminium, zinc, or iron, and so iron rather. And so magnesium metal will always displace aluminium, zinc, and iron from sulfate solutions in which they're found. So, when some metals react with water, the end product of the reaction can be a metal oxide and hydrogen gas. So, for example, when we react magnesium with water, we get magnesium oxide and hydrogen gas being evolved. So, in this case, the metal loses electrons, and so it's oxidized to its ionic form, and the hydrogen ions within the water will gain electrons and are reduced to form molecular hydrogen gas. The water is the substance that provides the metal with the oxygen, and so is said to be the oxidizing agent. The metal, on the other hand, is the substance that receives the oxygen, and so it's said to be the reducing agent. Now, when metals react with acids, which are molecules that dissociate to release hydrogen ions in solution, the products of the reaction are hydrogen gas and a metal compound containing ions of the metal and the conjugate ions from the acid. And so the ionic equation for this would be something like this. So the example being used here is calcium, but a similar reaction occurs for other metals that react with acids. So we see here that the metal loses electrons and so is oxidized to its ionic form, and the acid gains electrons, and the hydrogen ions from the acid will then form hydrogen gas. Now, electrolysis is something that we're going to cover later on in this webinar anyway, but for the moment, in the context of oxidation and reduction, we do need to mention it. So when metal compounds are either liquid or molten, or when they're in solution, they have the ability to conduct electricity. Now, the reason for this is because whether you're dealing with a molten ionic compound or with an aqueous ionic compound, a solution of an ionic compound in water, you have charged particles which are able to conduct an electric current. So the liquid in either case is called an electrolyte, and the process of splitting the compound is called electrolysis, because what we're doing is using an electric current to do the splitting. The word lysis means to split or to break apart. So many metals can be obtained from their compounds by electrolysis. A very important example of this is aluminium. So we can take aluminium oxide from aluminium ore, and we can extract it from that ore by melting down the aluminium oxide and then electrolyzing it. Sodium can also be extracted in this way from sodium chloride. So let's take a look now at some of the other topics that you requested that I go through. So this the next one will be the reactivity series. So in chemistry, we tend to group elements into a sense of order and pattern, and this helps us to study chemistry and also to make predictions concerning the chemical behavior of various elements. So the more reactive an element is, the more vigorous are its reactions, and conversely, the less reactive an element is, the less vigorous the reactions are. We're already familiar with the idea that certain elements are more reactive than others, but when many reactions are studied, there's a clear pattern of reactivity which starts to emerge, and we can then organize those elements into an order that we call the reactivity series. So the reactivity series of a group of elements is usually derived by carrying out a large number of experiments to see how vigorously various elements react with specific other elements or compounds, so air, water, and so on. So the reactivity series of metals, for example, can be worked out by seeing how vigorously the metals react with air, water, and dilute acids. So the majority of the elements in the periodic table are in fact metals, and so for the construction of the reactivity series of metals, we simply organize them in order of increasing vigorousness of reaction with these various different compounds. So this is an experiment that many of you will have already seen in the school science laboratory. We take a basin filled with water with a little bit of indicator solution in it usually, and we drop a piece of sodium into the water and observe how that sodium reacts. And the sodium rapidly will melt into a ball of molten sodium due to the heat energy released by the reaction. It also releases hydrogen gas as it fizzes and bubbles away, and it leaves behind an alkaline solution. Now, potassium, being in the same group, will have a similar reaction, which will also produce hydrogen gas and also will leave an alkaline solution. However, its reaction is much more vigorous. So we drop the potassium into the water, and the reaction is so vigorous that it produces a characteristic kind of lilac-coloured flame and can even pop out of the water. And so it is a much more vigorous reaction because potassium is more reactive than sodium. So many metals have shiny surfaces. Now, these surfaces eventually will build up a layer of oxide as that metal reacts with atmospheric oxygen. So we say that in common language, we say that the surface of the metal is becoming tarnished. So many metals will actually burn in air as well. They react with the oxygen forming metal oxide, and some metals will burn more readily than others. So if we were to take a piece of sodium and burn it in the atmosphere to observe its reaction with atmospheric oxygen, it reacts pretty vigorously, as we'll see here. And it will leave a layer of oxide, sodium oxide, on the surface of the metal. But freshly cut pieces of sodium, which is a rather soft metal, have rather shiny looking surfaces, but even as we watch, those surfaces will quickly become dull and tarnished looking because the cut surface of the sodium is rapidly reacting with atmospheric oxygen to form sodium oxide. So, due to its reactivity with atmospheric oxygen, typically sodium metal will be stored under oil to prevent it from reacting with oxygen in the atmosphere. Now, one of the reactions which you've almost certainly observed in the science laboratory, and we have mentioned before in previous chemistry webinars, is the reaction of magnesium metal when burned in air. Now, magnesium is another very reactive metal, and it burns with a brilliant white flame. Now, when the reaction is over, you can see the white deposit of magnesium oxide on the surface of the tongs and also on the Bunsen mat. So, not all metals will react as vigorously as sodium and magnesium. Zinc, for example, does react with oxygen, forming zinc oxide, but the reaction is not very vigorous. So, silver and gold also are metals in the reactivity series. However, they're so unreactive that they don't react with oxygen even if heated strongly. So as a result of heating metals in the presence of oxygen, the metals can be organized into a series by putting the most reactive metals at the top and the least reactive metals at the bottom. So the reaction of metals with oxygen can be used to arrange them, in other words, in a reactivity series, something like this. So we have the most reactive metals, which will burn easily with a bright coloured flame to form their respective oxides. We then have slightly less reactive metals that will react slowly when heated with oxygen. We have some metals that only react when the metal is very, very hot indeed. And then we have metals such as silver and gold, which show no reaction at all with atmospheric oxygen. And so in all cases, if there is a reaction, the reaction is between the metal and oxygen to form a metal oxide. So if a metal reacts with water, typically hydrogen gas is produced. So reactive metals will react with cold water to form hydroxides. Less reactive metals may not react with cold water, but will react with steam to form their respective oxides. And so these are the word equations for those two general types of reactions. Now, in both cases, hydrogen gas is invisible, but can be tested for using the so-called squeaky pop test. So here's one such example. So if we were to take calcium and react it with water, let's turn all the labels on here, we'll see that it will form bubbles of hydrogen, which we can then trap in this upturned boiling tube. And the reaction is relatively slow, and eventually we can test for the presence of hydrogen gas here by bringing a lit splint or a glowing splint over to the mouth of the beaker, and this will produce our squeaky pop. Alright, so another metal that we can test in this way is zinc. Zinc is lower in the reactivity series than calcium, and we find that when we test this metal, the zinc will show very little, if no, reaction with water. However, what we can do is we can blow very hot steam past the zinc, and this will cause a reaction to take place. And so in this case, the steam molecules, the water molecules in the vapor state, have more average kinetic energy with which to overcome the activation energy barrier for the reaction and actually react with the zinc to form the zinc oxide and hydrogen gas. And again, we can test for the presence of hydrogen gas by bringing a lit splint to the mouth of the tube, which will then give us a squeaky pop sound. So, in general, with metals, the alkali metals, the group 1 metals, the reactivity of those metals increases as the group is descended. So, the reactions of the alkali metals with water are generally quite vigorous, but they become more and more vigorous as you descend the group. So, when lithium reacts with cold water, it produces hydrogen gas, which causes the metal to energetically move around on the surface of the water. And so once again, this reaction is forming an alkaline solution of lithium hydroxide, and also the bubbles that you're seeing is the hydrogen gas, which is being produced by the reaction. So if we were to go down to the next metals in the series as we go down the group, sodium reacts with cold water by fizzing and bubbling and producing hydrogen gas, which then causes the metal to move around the surface of the water somewhat more energetically than lithium does. But the heat generated by the reaction is enough to melt the sodium to form a ball of liquid metal, which you're seeing here as it whizzes around the surface of the water. So the sodium metal in the liquid state is less dense than the water and floats around on the surface. So here is the reaction and the balance symbol equation for this. So it's important for you to memorize these general reactions of metals and metal compounds with these various substances so that you can then apply those to write the balance symbol equation for those reactions should they arise in exam questions. So if we go to potassium, again, we see a much more vigorous reaction this time, even more than sodium, because again, potassium is lower in the group than sodium is and will therefore react more vigorously. So the reaction of metals with either cold water or steam can be used again to arrange them in a reactivity series. And once again, we see the same order emerge. So these ones will react with cold water. These will only react when you heat the water to make steam. These will not react with water or steam, but in all cases, you either have the metal reacting with water to form a metal hydroxide plus hydrogen, or you have the metal reacting with water, in the case of these metals here, to form the metal oxide plus hydrogen. And again, it's very important that you memorize these general equations for these reactions. So metals can also react with dilute acids to form a salt and hydrogen. Any metal compound that's made as a result of a reaction occurring between a metal and an acid is called a salt. So this is the general equation. Now, in fact, it would be very dangerous to react highly reactive metals such as sodium and potassium, even with dilute acid, because these reactions are extremely vigorous, very violent. So we react the metal with an acid, and we always get a metal compound called a salt plus hydrogen. But in the case of things like sodium, the group 1 metals, generally speaking, we don't do this in the laboratory because the reaction gives off so much energy, it can be quite dangerous. So a salt is always formed when an acid reacts with a metal oxide, a metal hydroxide, or a metal carbonate. So if we compare how quickly these metals react, we would expect the least reactive metal to react least vigorously and the most reactive metal to react most vigorously. But in all cases, the overall general equation that describes those reactions is always the same. So the reactions of metals with dilute acids again can be used to arrange them in order of reactivity. Once again, we see that the most reactive elements are found near the top, and these will react extremely violently. The next most reactive will react reasonably well, and then you also get the metals, the least reactive metals, not reacting with dilute acids at all. So in all cases, the metal reacts with an acid to form a salt and hydrogen whenever you do get a reaction. So again, this order that we're seeing emerge from ordering the vigorousness of the reactions of these metals with various compounds and other substances, this is referred to as the reactivity series. So to summarize, we have the order of reactivity of the metals, and we have the various ways in which these metals will react with either oxygen, with water, or with dilute acids. Now, in all cases, you do need to be aware of the general equations that describe these reactions so that you can then construct balanced symbol equations for the reactions of specific metals with specific other substances if presented or if required to do so in an exam question. So the reactivity series of metals can also be used to determine whether or not one metal will displace another metal from a compound. Now, always the more reactive metal will displace the less reactive metal from the compound of that less reactive metal. So an example that we've seen already is the iron nail being inserted into a beaker of copper sulfate solution. Iron is more reactive, and so iron will enter the solution to form iron sulfate, and in doing so it will displace the copper ions from that copper sulfate solution to form metallic copper. But if we place a strip of copper into magnesium sulfate solution, we don't get a reaction because in this case the substance in the compound, or the metal in the compound, magnesium, is higher in the reactivity series than copper. So in this way we can use the reactivity series to predict whether or not a displacement reaction would occur. So again, in this table we see whether or not we get displacement reactions from the metallic elements when they are placed into solutions of the compounds of those metals. So magnesium will displace aluminium. It will also displace zinc, iron and copper because magnesium is higher in the reactivity series than any of these metals. Now if we do the other reactions, we find that again it is only in the case where you have a more reactive metal that it will displace the less reactive metal from its compound. Now, a particularly spectacular and violent reaction that you may or may not have seen demonstrated is the so-called thermite reaction. Now, thermite is a mixture of aluminium and iron oxide powders. So this is thermite. What you have here is finely blended aluminium powder and iron oxide powder, and it looks like this. So aluminium is more reactive than iron and is therefore higher up in the reactivity series than iron. So when a mixture of aluminium and iron oxide is heated, a very vigorous exothermic displacement reaction occurs, where the aluminium displaces the iron from the iron oxide. So a great deal of heat is given out, and this is sufficient, in fact, to melt the iron that is displaced. So this reaction is called the thermite reaction and is actually used in industry for welding purposes. So for example, to weld railway lines together as the track is laid. It's also used to cut through very large steel girders because again, the heat which is which is given out by this reaction, is so high that it can melt iron. So here we can see the thermite reaction being used to weld together two sections of track. So, often what you will see in the reactivity series is a couple of non-metals making an appearance. Now, usually the reactivity series of metals will be will have carbon and hydrogen shown somewhere in them. Carbon and hydrogen, however, are both non-metals, but they can take part in displacement reactions. So if carbon and hydrogen are heated, they can displace some metals from their oxides, and in fact this is a very important way that metals are extracted from their ores, many of which are oxide compounds. So if you heat carbon with a metal oxide, sometimes what can happen is that the carbon can displace the metal from the oxide to form carbon dioxide, and this leaves behind the pure metal. Hydrogen can do much the same thing. In this case, it leaves behind the pure metal and water, because the hydrogen displaces the metal from the oxide to form the oxide of hydrogen, which is water, dihydrogen monoxide, H2O. So carbon and hydrogen will only displace metals lower than themselves in the reactivity series. So this diagram here, this animation, shows how hydrogen can be used to displace a metal such as copper from its oxide. The displacement reaction takes place because, let me turn the labels on here, because copper as a metal is less reactive than hydrogen, and so as the hydrogen blows past this copper oxide and we heat the copper oxide from underneath by a Bunsen flame, we start to see a change in colour as the hydrogen displaces the copper from the oxide to form water, which then condenses at this end of the tube, and this leaves behind a lump of pure copper. Now the excess hydrogen is burned at the other end of the tube to prevent it from inflating and breaking the tube due to excess pressure. So the complete reactivity series is often includes carbon and hydrogen for this reason. So we have the various metals and their symbols, but we also have carbon and hydrogen placed into this series, even though they themselves are non-metals. So the next topic that you all asked me to cover was electrolysis, so let's now move on to that. Okay, so ionic equations are something that many of you asked me questions about in the lead up to this webinar. Now, ionic equations are a form of chemical equation describing a chemical change. So in all chemical equations, the reactants are always written on the left, and the arrow signifies a change that takes place in which the reactants turn into the products, which are displayed on the right hand side. And so here's a familiar equation where we see the reactants on the left and the product on the right. However, ionic equations also require you to know the ionic charges that the particular ions that you find in the reactants and or products possess. So state symbols are also important. So when writing ionic equations, there are 4 state symbols that show the physical states of the reactants and products. So to remind you, we have L for liquid, S for solid, G for gas, and AQ for aqueous solution, which means dissolved in water. The state symbols should be written in brackets after each reactant and product. So here's a couple of examples. So let's look at the way in which we construct ionic equations. So sodium chloride is an ionic compound composed of sodium ions and chloride ions. So we have 2 elements, sodium and chlorine, in where the atoms have formed ions, positive and negative respectively, and these are bonded together by ionic bonds. So sodium chloride is formed when you take sodium metal, the element, and you burn it in chlorine gas, again an element. So sometimes the ionic compounds formed as a result of a chemical reaction are written in their ionic form. So we can either write the formula for sodium chloride like this, or we can show what are the charges of the ions within that formula. So we have a unipositive sodium ion and we have a uninegative chloride ion. So this is the overall equation, but when this equation is written in its ionic form, it looks like this. So the ions comprising the sodium chloride can also be written separately. like this. So here's something for those of you in attendance to try for yourselves. Try balancing the following equation and then writing it in ionic form. So I'm going to pause here and let you guys answer this question. It should pop up on your screen. Those of you who don't see it on your screen, you can go ahead and type your answer in the chat box. I'm going to pause here and let you guys have a go at this. All right, so let's take a look at how this is done. So firstly, the balanced symbol equation, you would need the formulae for these substances. So NaOH for sodium hydroxide, MgCl2 for magnesium chloride, NaCl for sodium chloride, and Mg with OH in brackets and a 2 as a subscript outside of the brackets for magnesium hydroxide. You would then balance the equation like this. So well done to those of you who got that right. Now the ionic version of this equation would look something like this. So we have 2 sodium ions in each sodium hydroxide, or rather we have 1 sodium ion in each sodium hydroxide formula unit. So if we have 2 of these, we have 2 sodium ions. For similar reasons, we have 2 hydroxide ions because there's only 1 hydroxide ion in each formula unit of sodium hydroxide. We also have magnesium chloride. Now magnesium is in group 2, so it forms Mg2+, which means you need 2 chloride ions in each formula unit to balance the charge on the magnesium ions, and so this would be 2Cl- here. And on this side of the equation, among the products, we have 2 formula units of sodium chloride, each of which contains 1 sodium ion and 1 chloride ion. So we would write those separately like this. And in magnesium hydroxide, once again, each hydroxide ion has a single negative charge on it. And so if magnesium is Mg2+, we're going to need 2 hydroxide ions. We have 1 formula unit of this on the right-hand side of the equation. So we have 1 magnesium ion and 2 hydroxide ions. Well done. So now that we talked about ionic equations, let's look at electrolysis and how ionic equations describe oxidation and reduction at the electrodes of an electrolytic cell. So electrolysis, again, is the chemical decomposition of an ionic compound by direct electrical current, and it's performed in a device called an electrolytic cell. So this animation shows essentially what's happening in a generalized electrolytic cell. Now again, the electrolyte can be either molten or aqueous. So this can be a molten ionic compound, in other words, an ionic substance which has been melted into the liquid state, or it can be an ionic compound which has been dissolved in water in the aqueous state. Either way, you have mobile charge carriers, positive and negative ions, which are free to move. The negative ions are attracted to the positive electrode, which is called the anode, and the positive ions are attracted to the negative electrode called the cathode. At the positive electrode, the anode, the negative ions will give up their excess electrons, which then flow into the circuit. They are given the electromotive force to move around the circuit by the direct current power supply, and they flow round to the cathode, the negative electrode, and on the surface of the cathode, the positive ions which are attracted to it gain the electrons from the cathode to form the element. So this is the general case. This is what's happening in a generalized electrolytic cell. So the negative ions migrate towards the positive electrode. The positive electrode is referred to as the anode. The positive ions, or the cations, migrate to the negative electrode called the cathode. So please be familiar with these terms. Once again, I do see a lot of students dropping marks or not gaining marks due to the incorrect use of these terms. Negative ions are referred to as anions because they migrate towards the positive electrode, which is referred to as the anode. Positive ions are referred to as cations, again because they migrate towards the negative electrode, which is called the cathode. So let's take a closer look at what's happening at each one of these electrodes. So at the anode, firstly, at the positive electrode, the anions, the negative ions, will surrender their electrons, their excess electrons, which then flow into the circuit. Now these anions become electrically neutral because they've given up their excess electrons. So the anions become electrically neutral atoms. So the general equation for this, in general, is that if you have a negatively charged anion, which is Y-, this becomes a neutral atom of Y, whatever element that is, plus the electron or electrons which are released into the circuit. So this is called oxidation because the negative ion has lost electrons. Now, if we contrast this to what's happening at the positive electrode, we can also write a general equation to describe what's happening there to the cation. So at the cathode, the negative electrode, the cations, the positive ions, which are attracted to the negative electrode, will gain the electrons which have come round the circuit and will form, again, neutral atoms. So in this case, if we have positive ions, X+, these gain electrons to form neutral atoms of element X, and so this would be described as reduction, the gain of electrons. So one of the examples that you should all be familiar with is the electrolysis of molten sodium chloride. Now please be careful because the equation and what happens to molten sodium chloride when it's electrolyzed is very different from what happens when you take an aqueous solution of sodium chloride. So let's look at molten sodium chloride first. So when we melt sodium chloride, it becomes a liquid in which the sodium ions and the chloride ions are free to move independently. So we draw half equations like the ones that you saw in the last couple of slides to show the changes that occur at the positive and the negative electrodes. Now, as always with chemical equations, both sides of the equation must balance both in terms of the numbers of atoms or ions and the numbers of electrons. So during electrolysis at the anode, again, in this case, the anode is going to attract the negative ions, and so the negative ions are going to give up their electrons to form neutral atoms. However, chlorine atoms, being in group 7, have 7 electrons in their outermost shells and therefore will form diatomic molecules of chlorine, and so each element will form its element in its standard state at each one of the electrodes. So if chlorine is in group 7, we're going to form chlorine atoms at the anode. However, those chlorine atoms are not just going to sit there as chlorine atoms, because chlorine atoms are unstable because they have 7 electrons in their outermost shells. Each chlorine atom is going to form a covalent bond with another chlorine atom to form diatomic molecules of chlorine. And so in this case, we're going to need 2 chloride ions, each of which gives up 1 electron, so we end up with 2 electrons on the right hand side of this half equation, and the chlorine atoms become neutral chlorine, or the chloride ions become neutral chlorine atoms which bond with each other to form chlorine gas molecules. So chlorine gas is formed at the anode. So we see here that the ions have formed the element. Now at the cathode, the positively charged sodium ions, which are in the liquid state, are going to gain electrons to form sodium atoms. And so the sodium atoms are going to be formed in the solid state, and so sodium metal is formed at the cathode. So if we now visualize what's happening, we have molten sodium chloride. Again, this is sodium chloride in the liquid state, not dissolved in water. And we see that sodium metal is being deposited on the surface of the cathode, while chlorine gas, these bubbles of green gas, are forming at the anode. So when molten, sodium and chloride ions become free to move, and the electric current is able to flow through the circuit because you have a constant entry point of electrons at the anode, and you also have electrons flowing out of the circuit at the cathode. And so as long as electrons are moving, we have an electric current flowing, and this is made possible by the fact that the ions in the liquid are free to move. Now if we compare this to what happens when we put the sodium chloride in aqueous solution and use that as our electrolyte, we get different products. So a solution of sodium chloride, sometimes called brine, can also act as an electrolyte. Now during the electrolysis of brine, we actually produce 3 important substances. So here is the overall reaction for what happens. So we have sodium chloride reacting with the water in the solution to form sodium hydroxide solution, aqueous solution, and we also get 2 gases being formed, hydrogen gas and chlorine gas. So the sodium chloride will contribute sodium and chloride ions to the electrolyte. In addition to this, the water will also provide hydrogen ions and hydroxide ions to the electrolyte. Both the hydrogen and the sodium ions are attracted to the cathode because they're positively charged and the cathode is negatively charged, but the sodium ions in this case will stay in solution. You don't get the production of sodium metal in this case. So here is the reaction which is happening at the cathode. So it's the hydrogen ions which are gaining electrons, this time to form hydrogen molecules at the cathode. So both chloride and hydroxide ions are attracted to the anode. However, the hydroxide stays in solution, whereas the chloride ions will form chlorine gas, as is being shown here. So the chlorine gas will have traces of oxygen within it, which is caused by the presence of hydroxide ions at the anode. So this means that the electrolysis of sodium chloride solution, or brine, produces hydrogen, chlorine and sodium hydroxide, and these are all important reagents in chemical reactions and are valuable. So here is a diagram showing, or rather an animation showing the electrolysis this time of sodium chloride in aqueous solution. So we start with brine, but what we end up with is a solution containing sodium and hydroxide ions. As you can see, the sodium ions and the hydroxide ions are not interacting with either the anode or the cathode, but the chloride ions are forming chlorine gas at the anode and the hydrogen ions are forming hydrogen gas at the cathode. And so in this manner we produce three very important substances by the electrolysis of sodium chloride solution, or brine. Okay, so there can sometimes be impurities which are introduced when we electrolyze the aqueous solutions of some ionic substances because of the presence of water. So if two types of cations are present in the electrolyte, then a competition reaction will take place at the cathode. The relative positions of the metal and hydrogen ions from water in the reactivity series will then determine which of those elements is being formed at the cathode. So the element which is lowest in the table of those two, either hydrogen or whichever metal element is present in the solution, is going to be the one which is produced in its elemental form at the cathode. So in a solution of sodium chloride, as we saw, sodium ions from the sodium chloride and hydrogen ions from the water will both be present. Hydrogen is present lower down in the reactivity series than sodium, and so it's hydrogen gas which is produced at the cathode for that reason. Now, if we similarly take an aqueous solution of silver chloride, then silver and hydrogen ions are both going to be the cations which are present, the positive ions which are present in that solution. So silver is lower in the table in the reactivity series, and again it's going to be silver for that reason, which is going to be formed as an element, as a metal at the cathode. Now conversely, if an anion is present in an aqueous solution and that ion is nitrate, NO3-, or sulfate, SO4-2-, then oxygen will also be produced at the anode. If the anion present in the aqueous solution is a halide ion, such as chloride, bromide, iodide, and so on, the halogen, the group 7 element in its diatomic molecules, will be formed at the anode. So if we take a solution of hydrochloric acid and put it into an electrolytic cell, we'll find that it's actually a very good electrolyte. In aqueous solution, HCl dissociates to form hydrogen ions and chloride ions, as being shown here. Now, because we're dealing with an aqueous solution, we also have water molecules present, and the water molecules will weakly dissociate to form small quantities of both hydroxide ions and also hydrogen ions again. So here we have two sources of hydrogen ions from the dissociation of the hydrochloric acid and from the dissociation of water molecules, but we also have the presence of two anions. So we have chloride and hydroxide. So in both cases, the hydrogen ions from both of these substances are going to be attracted to the cathode, and there they will form hydrogen gas. The chloride ions are attracted towards the anode, and because we have a halide present, it's going to be the chloride ions which form chlorine gas. But the chlorine gas may have traces of oxygen within it, because what also happens at the anode is that the hydroxide ions will give up electrons to form both oxygen gas and also more water molecules. So this means that the electrolysis of hydrochloric acid primarily produces hydrogen gas and chlorine gas, whereas the electrolysis of very weak hydrochloric acid, in other words hydrochloric acid which has larger quantities of water per unit volume, will also produce hydrogen gas and oxygen gas. So this animation summarizes that process where we're getting hydrogen at the cathode and chlorine at the anode, and this leaves behind a solution containing hydroxide ions. Now, water is a very weak electrolyte. It doesn't conduct electricity particularly well, but in order to make it conduct electricity better, we can add a few drops of dilute sulfuric acid solution. We then pass an electric current through our electrolytic cell, and we find that at the anode we're producing a steady stream of bubbles of oxygen, whereas at the cathode we're producing a steady stream of bubbles of hydrogen. So the overall reaction for the electrolysis of water can be shown like this. It is a reversible reaction. Now, in order to show what's happening at each of the electrodes, we need to make use of half equations. And so at the cathode, we have the production of hydrogen gas by the addition of electrons to hydrogen ions. So the hydrogen ions are becoming reduced to form hydrogen gas. And at the anode, we have hydroxide ions, which are giving up electrons to form oxygen and more water molecules. Okay everyone, it seems like we've reached the end of the first hour here, so I'm going to pause for a 5-minute break. After the 5-minute break, you should be, those of you in attendance should see a poll pop up on your screen where you'll be able to vote as to whether you'd like me to continue for the next hour by covering exam questions, which you all received in your exam style questions pack for this webinar, or whether you'd like me to continue covering the teaching of this topic, going through the ideas in the order in which you voted for them. But either way, we'll take a 5-minute break and then we'll do whatever it is that you voted most for afterwards. So I'll see you in 5 minutes time. Okay, so we're back after the second 5-minute break here. Let me have a look at what you guys have voted for me to do. Okay, so it seems, like across all of the different student groups in attendance, the vast majority of you have voted for me to continue with the topic teaching, so I will continue to do that. Again, just please be aware that if you do require the answers to the exam questions in the exam questions pack, please do just log into the website and then go to the webinar resources page, which the attendees have been given access to, and you'll find the mark scheme on that page within 48 hours of the end of this event. If you continue to have any questions about either those exam questions or about any of the topics that we're covering during the course of these first 2 hours, then you can also send me that question as a public question on the live chat, where you can perhaps get a discussion going with other students, or alternatively you can send me that question as a private message, and I'll generally get back to you within 24 to 48 hours, and that will remain open up until the end of the exam period in late June. Alright, so one of the other electrolytic reactions that you need to be aware of is the electrolysis of copper chloride solution. So in this reaction, copper atoms are released at the negative electrode and chlorine molecules at the positive electrode. So here's something for you all to try. Let me just bring up that poll question on your screens here. If you don't see this question pop up on your screen, then go ahead and type in chat your answer. So write balanced half equations to show what happens at the anode and at the cathode. So I'm going to pause here and let you guys answer that question. Alright, so here's the solution to that question. So at the anode, given the information that you've just been given, chloride ions will lose electrons to become chlorine molecules, and so the half equation for that would be this. And at the cathode, copper ions will gain electrons to become copper atoms, and so this is what you would see happening at the cathode. So this animation summarizes what's going on. So we're starting with copper chloride solution. In aqueous solution, the chloride ions move towards the anode where they give up their excess electrons, and then the uncharged electrically neutral chlorine atoms will covalently bond in pairs to form chlorine gas. At the same time, at the cathode, the positively charged copper-2 ions will be attracted to the negatively charged cathode and will gain electrons to form a deposit of copper metal. So this is the kind of summary, the animation to show or to summarize that process. Now another solution that you need to be familiar with the electrolysis of is the electrolysis of copper sulfate. Now when we're using copper electrodes, we can use this process to purify an impure sample of copper to form purified copper. And the way that it works is something like this. So what's happening here is that the anode will lose mass as the solid copper of the anode is dissolving to form a solution of copper-2 ions. Let me reset that. And so the anode, the copper from the anode, is steadily dissolving and forming copper ions, which then migrate towards the cathode, where they gain electrons to form a deposit of purified copper metal. So the cathode gains mass as the copper is added to the surface from the solution. Now the mass gained by the cathode is equal to the mass lost by the anode. So if we, instead of using copper electrodes, if we use carbon or graphite electrodes instead for the electrolysis of copper sulfate solution, we end up with a slightly different outcome. So in this case, oxygen gas is being produced at the anode. The cathode will gain mass as copper is added to the surface from the solution. So the electrolyte copper sulfate solution will gradually change to a dilute solution of sulfuric acid for this reason. So once again, at the anode, we have this half equation which shows the formation of copper ions from solid copper. At the cathode, we have a different half equation showing where these copper ions gain electrons to form copper atoms or copper metal. So the amount of products produced during electrolysis will depend upon, firstly, the time that the current is passed for. The amount of current passed as well will also determine the the amount of product produced. Now, one of the applications of electrolysis is electroplating. So here you're seeing a surface of EPNS, which stands for electroplated nickel silver. So this is an object made of the metal nickel, which has been plated with a very thin layer of silver. And metal objects can be plated with gold, silver, copper, or other metals, again using electrolysis. So here is a piece of zinc foil being plated with copper. Now, the way that electroplating with copper works is very similar to the purification of copper that you saw earlier on. This time we have a cathode made up of a different metal. The anode, once again, is a piece of impure copper, which is used eventually to plate the surface of the other metal at the cathode with a layer of copper. And so what ends up happening is that the electrolyte, a solution of a copper salt, such as copper sulfate, allows for the transfer of copper ions which are formed as the copper atoms in the impure copper anode give up electrons. These copper ions go into the solution and then migrate towards the oppositely charged negative metal cathode, forming a coating of copper on the surface here. So once again, at the anode, we have the formation of copper ions by the oxidation of copper. So copper is giving up electrons, it is being oxidized to form copper ions which go into aqueous solution. But at the cathode, those same copper ions are gaining electrodes at the surface of that metal cathode to form a layer of copper metal. So a similar approach can be used to plate various objects with a variety of different metals. And so we can use chromium plating. And so these are various parts of motor vehicles which have been chrome plated. We can also use the same process to plate various objects with gold and silver as well. So everything that we've been talking about, oxidation, reduction, electrolysis, these are all relevant to another of these topics that many of you voted for me to cover, which is the extraction of metals. How do we get purified metals from metal compounds which are found in the natural ores which you find in rocks? So unreactive metals such as gold can be found in their native state, in other words as pure uncombined metals in riverbeds or by mining. So we see here some examples of gold mines and a nugget of pure gold. Now today most gold has to be mined from deep underground in countries such as South Africa. So a few metals at the lower end of the reactivity series can be found as pure metals in rocks, and this includes gold. Gold is one of the few metals which can be found pure in nature, and the reason for this is because it's so chemically unreactive that it will not easily form compounds, and so you'll find it as a pure metal, typically panned or mined in stream sediments. Chromium can also be found pure in nature, so this photo shows a large single crystal of chromium metal. Copper is not usually found in pure form because it's not low enough in the reactivity series. In rare cases, it may be found pure in nature, usually in volcanic areas. So most metals are extracted from rocks which contain large enough quantities of metal compounds by weight to make it economically viable for them to be extracted. So such mineral deposits containing these metal compounds are called ores, if it's economically worthwhile to extract the metal from them. So malachite, shown here, this is a copper ore. Now the green colour is due to copper carbonate. Copper is also found in various other ores as well. Here we can see galena, which is an ore of lead. The metallic appearance of the ore is due to the high percentage of metal found in those compounds. So two common iron ores are magnetite and hematite. So here we can see a chunk of magnetite, and this is hematite. So hematite is the ore commonly used in blast furnaces, and iron can also be found in other ores such as iron pyrites. Now iron pyrites have an appearance which has often led them to be confused with gold. This is sometimes called fool's gold. So these golden crystals in this rock sample are not actually gold but iron pyrites. So these are really iron disulfides. Now, the discovery of techniques to extract metals in bulk from their ores was a major contributing factor to the Industrial Revolution. So this iron bridge in Shropshire was built in 1789. So metal ores must contain enough metal present in the ore to make extraction economically viable. So as more of the ore is extracted by mining, there's a pressure on the value of the metal to increase. This can make it economical to extract metal from the ores where it was not previously economical. Now the ease of extraction of a metal from its ore depends upon the position of the metal within the reactivity series. So again, to remind you of the reactivity series, we see it here on the right. Again, the metals at the bottom of the series, such as gold, can be found in their pure form in nature, or can be produced by simply heating the ores to cause them to chemically decompose. So here's an example. Cinnabar, which is mercury sulfide, can release metallic mercury simply by heating it. So we have mercuric sulfide, and it reacts with oxygen under heating to form mercury metal and sulfur dioxide. So here would be the symbol equation. Now the metals in the middle of the series below carbon, such as zinc, iron and lead, these can be obtained by heating the metal oxide with a form of coal called coke. Now this has been heated to remove impurities, or coal, when we heat it to remove the hydrocarbon impurities, we're left with a form of carbon called coke. So the metals at the top of the reactivity series, such as sodium, aluminium and so on, these have to be extracted by electrolysis of the molten compounds such as chlorides or oxides. So let's take a look at the extraction of iron. So here we can see the typical surface appearance of hematite. So if a metal occurs in nature as an ore, it has to be extracted from the ore before it can be used as a pure metal. Hematite is iron 3 oxide, so it contains iron ions with three positive charges, and so the formula for iron 3 oxide would be this. Now hematite is reduced to metallic iron in the blast furnace by reaction with carbon monoxide. The carbon monoxide in turn is produced when carbon in the form of charcoal is heated in oxygen. So we have iron 3 oxide reacting with carbon monoxide to release metallic iron and carbon dioxide. The balance symbol equation for this would be shown here. So the production of iron in the blast furnace produces 96% pure iron. A basic oxygen furnace is then used to remove the remaining impurities, and during that process a small amount of carbon, up to about 2%, is left in the iron, which produces steel. So let's take a look at what actually happens in the blast furnace. So molten iron is tapped from the bottom of the blast furnace. Now, this is then allowed to set and solidify into blocks which are called pigs. Now they're called pigs because they're roughly cylindrical blocks which have these little legs which are deliberately they're cast into molds which are cylindrical with these 4 little legs at the bottom to allow them to stand upright and not roll over. And so this is why it's called pig iron. Now, the pig iron produced by this process is 96% pure, but the impurities make it brittle and of limited use as a structural material, and so it has to be purified further in an oxygen furnace. So here we see the blast furnace. We have blasts of hot air coming in at the bottom of the furnace to raise the temperature of the contents. We have the molten iron being tapped from the bottom, and the impurities, the molten impurities called slag, are siphoned off the top of the iron where they float, and you have a continuous supply of iron ore, limestone and coke to allow a constant input of the reactants into the furnace here. So the pig iron, the impurities in the pig iron are mainly carbon, sulfur and silicon and phosphorus. Now these impurities are removed in the basic oxygen furnace. So this is how the oxygen furnace works. We have hot molten pig iron, and we have a jet of oxygen being introduced near the bottom with a water-cooled oxygen lance. This then allows the impurities to react with the oxygen to form slag, and this leaves behind highly purified iron with small amounts of carbon in it, which produces steel. So, in the oxygen furnace, what's happening is that the impurities are all reacting with the oxygen to form oxides, which can either escape as gases or form a layer of impurities on the surface of the molten steel called slag. Now the equations for the reactions of sulfur and carbon with oxygen are these, and so carbon dioxide and sulfur dioxide are allowed to escape from the oxygen furnace, and these escape as waste gases. Now the phosphorus reacts with oxygen to form phosphorus oxide, and the silicon also reacts with the oxygen to form silicon dioxide. The phosphorus oxide and silicon dioxide then combine with the lime, the calcium carbonate, and the calcium hydroxide in the furnace to form this impure substance which separates from the steel called slag. So this is mainly calcium phosphate and calcium silicate, and this floats on the molten iron and can be poured away. The iron is then poured off later. So once the impurities have been removed, the structure of the iron itself will change, and the atoms form a regular arrangement of layers which can slide over each other, as shown in this animation here. So this change in structure makes the iron softer and easier to change shape. It makes it more malleable and ductile. However, at this point the iron is too soft for most uses, particularly if you're intending to use the iron as the basis for structural supports like girders, for example, in buildings. And so something else needs to be done to the iron to turn it into a much harder and stronger material for those uses. And this is where we convert the iron into steel. So to make a usable product from soft iron, it's converted into steel, which is an alloy of iron, by introducing specific amounts of different elements. So an alloy is a mixture of metals, which sometimes have one or more non-metallic elements added to them. So steel is made of 99% iron and about 1% carbon. Stainless steel is made up of around about 69% iron, 1% carbon, 20% chromium and 10% nickel. So these figures do vary from one type of steel to the next. There are various types of stainless steel, 316 stainless steel and so on, which are used for different purposes, but they're usually made from combinations of these elements in slightly varying proportions. Now the reason why steel is stronger is because of the change in the lattice structure of that alloy. So what we have here in steel is the iron atoms interspersed with larger atoms of other elements, and this causes the layers to be unable to slide over each other quite as easily as in pure iron. So the different sized atoms distort the regular layers of iron atoms, and this makes it more difficult for those layers to slide over each other. So converting metals into alloys will change their properties. Low carbon steels are easily shaped, whereas high carbon steels are much harder and stronger. So stainless steel is resistant to corrosion. In other words, it's resistant to chemical change by acids and other corrosive chemicals, and this makes it particularly suitable for certain things like dental caps, cooking pots, where it's preferable to aluminium, possibly for health reasons. So, various uses of different kinds of stainless steel being shown here. So, the extraction of copper. Now, copper is a transition metal which has properties that make it useful for things like electrical wiring and plumbing, and also other thermal applications like in cookware. So, we see the position of copper in the D block, or the transition metal block here, and we see some of the uses that copper is put to. So clearly, the extraction of copper from its various ores, such as malachite, is very important. So the way that we can extract copper is by forming a mixture of copper ore and carbon. And so what we're doing here is where we are displacing the copper from its compound, but this happens in two stages. First, the malachite, or copper carbonate, is thermally decomposed to produce another compound of copper, copper oxide. So copper carbonate will turn from a green substance to a black substance, copper oxide, and this happens under the influence simply of heating the copper carbonate. Now, in doing this, we are also releasing carbon dioxide gas. So you may have done a similar experiment or a similar chemical reaction in the laboratory. We can simply take copper carbonate, this green powder, and we can start heating it with a blue Bunsen flame directly, and we should be able to see the copper carbonate turning into copper oxide. And if we measure the mass of the copper oxide after the reaction is completed, we'll find that it's less than the mass of the original copper carbonate, because carbon dioxide has been lost to the atmosphere. So in industry, carbon is then used to reduce the copper oxide to form copper metal. So this is a reduction because the copper has lost oxygen atoms to the carbon, and so this forms purified copper metal. And this copper is then usually pure enough for most uses except for electrical components and wiring. Now, to further purify the copper for those purposes, it's first made into an impure sheet and then used as an anode in an electrolytic cell, as we saw in the previous animations here. So another reason to further purify the copper by electrolysis is that the impure copper plate has rare metals such as gold in it, which can be isolated after the electrolysis is complete. So once again, to remind you, we take the sheet of impure copper and we connect it in an electrical circuit as the anode to a pure metal copper cathode, and then we put both of those electrodes into an electrolyte of copper sulfate, and then we excuse me, and then we run the current through it. So what we see is the sheet of impure copper slowly losing its mass because the copper atoms are becoming copper ions. The copper ions migrate to the copper cathode. At the copper cathode, they gain electrons from the circuit to form layers of purified copper metal. Now, two other economically important metals which are extracted and purified by electrolysis are aluminium and titanium. So these are extremely useful metals. They're both low in density and also both relatively resistant to corrosion, and this makes them particularly useful in, among other things, the aircraft industry. Now, both metals are above carbon in the reactivity series, and so we can't extract them from their oxides by displacing them with carbon the way that we do with copper. So this means that their extraction tends to be quite expensive because, firstly, there are many stages in the process, and secondly, these processes tend to require large quantities of energy. So aluminium smelting plants, where we extract aluminium from its ore, are usually found relatively near to a port and a cheap supply of electricity, such as from a hydroelectric power station. So aluminium is extracted from its ore, which is called bauxite, by a method of electrolysis. So the aluminium is formed at the cathode, and this process requires a large amount of electricity, and this is part of the reason that aluminium is a relatively expensive metal. So I'm going to pause here and see if you guys can recall from your teaching in class what is the overall equation and or the half equations for the electrolysis of aluminium ore to form aluminium. So I'm going to pause here and let you guys answer that question. Again, you should see the question pop up on your screen here. If you don't, then go ahead and type your answer in the chat box. All right, lots of interesting answers. So let's go through how we can represent this process by equations. So first of all, we need to describe the actual ions which are present in the molten bauxite. Now, bauxite is made up of aluminium oxide, and the formula for aluminium oxide is Al2O3. Now, the reason for this is, again, that this is an ionic compound. Being an ionic compound, the metal, in this case aluminium, is going to form positive ions. The non-metal, oxygen, is going to form negative ions. Aluminium is in group 3, and therefore it will form Al3+. Oxygen is in group 6, and therefore it will form O2-. And so you're going to need 2 aluminium ions to balance the charges on 3 oxide ions, and vice versa. And so when this substance goes into the liquid state, when we melt this solid aluminium oxide, we're going to get a liquid in which we have 2 aluminium ions, 2 Al3+ ions for every 3 oxide ions, O2- ions. So at the cathode, the aluminium ions are going to gain electrons to form aluminium metal. So this is what's happening at the cathode, the half equation to describe what's happening at the cathode, and this is reduction because the aluminium ions are gaining electrons. Now at the anode, we have the oxide ions which are giving up electrons into the circuit to form oxygen, the element. Now oxygen being in group 6, each oxygen atom is going to double bond, form 2 covalent bonds with another oxygen atom to form diatomic molecules of oxygen. And so for this you need 2 oxide ions, and therefore these 2 oxide ions are going to release a total of 4 electrons into the circuit. Now the overall reaction for this, in order to do that, what you need is an equal number of electrons on the left and the right hand sides of the equations. So if you work through that, what you'll eventually get is this equation here. Now in order to do this, in order to construct an overall equation for the an electrolytic reaction, what you need to do is, first of all, you need to make sure that the number of electrons in each one of these equations is equal. And so the lowest common multiple of 3 and 4 is going to be 12. So we need to multiply this equation by 4 and this equation by 3. But then you add the left and the right hand sides together, and the 12 electrons on either side are going to cancel out. And then you're going to end up with 4 Al3+, and you're going to end up with 6 lots of oxide ions. You're also going to end up on this side with 3 oxygen molecules. So in order to balance the equation, you can then divide the numbers in front of each one of these reactants and products by the highest common denominator, and then you'll get this equation. So in summary, I realize that sounds a bit confusing, but basically what you need to do is you need to multiply through each one of these half equations by any whole number, which means that you have an equal number of electrons on the left-hand side of the cathode equation and an equal number of electrons on the right-hand side of the anode equation. You then add up all of the reactants on the left sides of both equations, put those on the left. You add up all of these together on the right-hand side of the overall equation, and then you cancel the electrons because you'll have 12 electrons on either side in this case, and then you divide the whole equation by the highest common denominator to get these numbers in front of your reactants and products. So the extraction of aluminium occurs in an electrolytic cell on an industrial scale that looks a bit like this. So what you have is a set of graphite anodes, and the receptacle, the actual chamber which carries the molten bauxite, has a lining which itself is the cathode. So the solid crust of electrolyte which forms on the surface is here, and you have carbon anodes as well as a carbon cathode lining the electrolytic cell. Around this you have insulation, because obviously you have a highly electrically charged cathode here, and this is all at a high temperature. Now what you'll find is that the molten aluminium is more dense than the molten bauxite, so it falls to the bottom where it can be siphoned off here. So this is the kind of simplified diagram of the extraction of aluminium on an industrial scale. Now, electrolysis on this type of scale can be incredibly expensive because it requires a lot of electricity. So for this reason, again, aluminium smelting plants have their own hydroelectric power stations built nearby so that the electricity can be made and supplied as cheaply as possible. Now, another reason why this process is very, very energy intensive and very expensive is that not only do you need large amounts of energy to power the electrical system which powers the electrolysis, but you also need large amounts of energy to heat the electrolyte material to a temperature where it will melt, and this is at around about 900 degrees centigrade. Now this can be reduced by the use of a substance called cryolite. The other thing is that the anodes, the graphite anodes, can also be used up in the process because at those temperatures they will react with the oxygen to form carbon dioxide, and so the anodes have to frequently be replaced in order to keep the process going. This constant replacement adds more cost to an already expensive process, and this in total causes the metal itself, aluminium, to be relatively expensive to buy. So here we have a summary of the process of aluminium extraction by the electrolysis of molten aluminium oxide from bauxite. So the ionic half equations for the electrolysis of the following molten substances are all obtained by a similar kind of logical method. So the first of these, aluminium oxide, we've already seen. At the anode we have this happening. We have 3 molecules of oxygen being formed because 6 oxide ions will give up all of their 12 electrons into the circuit. At the cathode, we have 4 aluminium ions gaining those 12 electrons to form 4 aluminium atoms in the liquid state. And so the overall reaction, we simply add all of everything that's on the left, forming aluminium oxide here, in the liquid form, which again will be composed of aluminium ions and oxide ions. And so if we have 6 oxides and 4 aluminiums, in these proportions, they combine to form 2 formula units of aluminium oxide. On the right hand side of the equation, we have 3 oxygens and we have 4 aluminiums. Now when we add the left hand sides and the right hand sides of these two half equations, we would have 12 electrons on the left versus 12 electrons on the right. So the electrons cancel and you don't show them in the overall equation. So here's something for you guys to try. What would be the half equations and the overall equation for the electrolysis of molten lead bromide? So I'm going to pause here and let you guys have a go at this question. Alright, so many of you have come up with the correct half equations and also the correct full equation, but for those of you who didn't get it, let's go through how this is done. So at the anode, we have 2 bromide ions. Again, this is in the liquid state, so in a liquid, the ions composing an ionic substance are free to move and exist separately in the liquid state. So we have 2 bromide ions. At the anode, they are going to give up their electrons in the circuit to form 2 bromine atoms. Bromine, being in group 7, will form diatomic molecules which are covalently bonded in order for those atoms to achieve stable outer shell configurations. And so 2 bromide ions will give up 2 electrons in total into the circuit at the anode to form 1 molecule of bromine gas. At the cathode, the single lead ion, so lead as an ion, is a dipositive ion, it's 2+, and so it will gain the 2 electrons from the circuit to form a lead atom in the liquid state. When we add the left and the right hand sides of these two half equations, we get the overall equation, which gives us PbBr2 is being split by electrolysis into the elements lead and bromine. So here's another one for you to try. what are the half equations and the overall equation which describes the electrolysis of lead iodide solution, or rather lead iodide in the liquid state, molten lead iodide? So I'm going to pause here, let you guys have a go at this. All right, yep, good. So many more of you this time got the correct answer. Well done. So let's have a look here. So this time at the anode, 2 iodide ions are giving up their electrons to form a molecule of iodine gas. At the cathode, we have again the same thing that was happening in the previous example. Each dipositive lead ion will gain 2 electrons to form the atom of lead in the liquid state. Again, we have an equal number of electrons on the left-hand side of the cathode half equation and on the right-hand side of the anode half equation. So we simply combine the left and the right-hand sides of these two equations together to form the overall equation for the reaction once again. Good. So one more example and then we'll move on. What about when we take molten potassium chloride? So what would be the half equations and what would be the overall equation for this electrolysis? All right, good. So here we go with the solution here. So at the anode, we've got 2 chloride ions, each of which give up 1 electron to form 2 chlorine atoms, which then bond with each other to form a diatomic chlorine molecule. The 2 electrons go into the circuit and then flow around to the cathode, where they are received by 2 potassium ions to form 2 potassium atoms in the liquid state. The 2 potassium atoms combine with the 2 chloride ion, the 2 chloride ions combine with the 2 potassium ions among the reactants to form 2 formula units of potassium chloride, and these form 2 atoms of potassium in the liquid state and 1 molecule of chlorine gas on the product side. Good. All right, now the next most highly voted for topic for me to cover is the topic of acids and bases, and so I'm going to move straight on to that. All right, so let's start with the idea of acids and bases and what we mean by an acid or a base in chemistry. So Svante Arrhenius, he was the first to develop the modern definition and the modern theory of acids and bases and alkalis. So he stated in his rather old-fashioned language that an acid is a substance that furnishes hydrogen ions in aqueous solution. And so the general formula for any acid will always contain hydrogen, and it contains some other ion called the conjugate ion of that acid, or the other part of the acid molecule. But when we place this in aqueous solution, the acid will dissociate to form free hydrogen ions, which are free to float around in aqueous solution, and the negatively charged remainder of the acid molecule is also in the aqueous state and free to move around. So this is called the conjugate ion of the acid. Now, conversely, he defined a base as a substance that produces excess hydroxide ions in solution. And so a base, when it combines with water, will form these ions, Hb+ and hydroxide ions. Now, Arrhenius's theory was not widely accepted at the time because it didn't explain the acidity and alkalinity of all substances. So, for example, sodium carbonate acts as a base but is not soluble. It doesn't produce hydroxide ions in solution. And so something more than Arrhenius's basic definitions were required. So, independent of each other, in 1923, Nicolaus Bronsted and Martin Lowry further developed Arrhenius's theory of acids and came up with what we now use as the definitions of acids and bases. So they proposed that an acid is a species that tends to donate or lose hydrogen ions or protons in aqueous solution, and a base has a tendency to gain or accept hydrogen ions and bond with them. So this theory explained more fully the behavior of acids and bases and is now the basis of today's theory of acids and bases. So an acid is a substance which gives up hydrogen ions, produces free hydrogen ions or protons in solution, and a base will bond with or accept hydrogen ions. So acids feature in our everyday lives and in industry. They can be found in many foods. They also play an important role in our bodies. Many of the fruits that we consume contain acids which give the fruits a slightly sour taste. So the name acids comes from the Latin word acidus, which means sour. So grapes, for example, contain tartaric acid. Citrus fruits such as oranges and lemons and grapefruits contain citric acid. Vinegar is a favourite flavouring added to fish and chips, and it's actually ethanoic acid, which has the old name acetic acid, which is produced by the bacterial fermentation of grape juice, which gives vinegar its characteristic taste and odour. Natural yogurt is made by the action of bacteria in milk, which produce lactic acid. The lactic acid makes the milk protein thicken and gives the product a slightly sour taste. Now, in commercial yogurt, the sour taste is often hidden by the addition of large amounts of sugars. Now, the human stomach has glands in its wall which also produces hydrochloric acid. Now, the acid has two main functions. It will firstly kill off pathogenic and other microorganisms present in the food, but it also provides the correct pH range for the action of the protease enzyme pepsin to start to digest proteins into peptides. So the human stomach acid is actually hydrochloric acid. And although natural acids such as citric acid and ethanoic acids are relatively safe, there are others which are termed mineral acids, which, although they're useful in science and industry, can be very dangerous, particularly when they're highly concentrated. So here are some examples of mineral acids: sulfuric acid, hydrochloric acid, nitric acid. These all need to be treated with caution, particularly when they're concentrated. Now, these are known as mineral acids. So car batteries often contain sulfuric acid. Sulfuric acid is also used in the etching process, which is used in industry to produce printed circuit boards. So an acid is a compound that forms hydrogen ions when it's added to water, and it's the hydrogen ions, H+, which are responsible for the characteristic properties of all acids. All acids will donate hydrogen ions, which are protons, and therefore acids can be defined as proton donors. The more hydrogen ions an acid produces when it dissolves in water, the stronger the acid is and the lower its pH value. All acidic solutions contain ions, and so they do conduct electricity. All acids will produce hydrogen gas at the cathode during electrolysis, and all strong acids are completely ionized in water. And so here we can see the formulae and names, and also the ions produced by three of the more common mineral acids. These are all strong acids because in aqueous solution the acid molecules are almost all dissociated to form hydrogen ions and whatever the conjugate ion of the acid is. So the conjugate ion of hydrochloric acid is chloride, the conjugate ion of sulfuric acid is sulfate, and for nitric acid the conjugate ion is the nitrate ion. So these are the weaker acids. These tend to dissociate to produce hydrogen ions, but they don't dissociate completely. So many of the acid molecules in aqueous solution are undissociated. So the more hydrogen ions an acid produces, the stronger the acid is and the lower its pH value. These acids tend not to dissociate quite as strongly as the ones that you saw in the previous slide, but they all have similar properties to the other acids. So in many ways, bases are the chemical opposites of acids. So there are many examples of bases in the home. So traditional toothpaste contains calcium carbonate as a base. Some oven cleaners contain the base sodium hydroxide. Now, sodium hydroxide is also an alkali because bases such as sodium hydroxide can dissolve in water. So a base which is water soluble is referred to as an alkali. So some of these bases, such as sodium hydroxide, typically will have a soapy feel to them because they start to break down the oils present in your skin. Now, this can be harmful if the base is present in high concentrations, such as in oven cleaners. And this is why it's very important to wear protective gloves when you're using oven cleaners and other substances around the home that contain strong bases present in high concentrations. Now, calcium carbonate, which is the main component of limestone, and also calcium hydroxide, which is found in slaked lime, can be used to neutralize the acids in acidic soils. The same neutralization reaction can be used to neutralize excess acid in the stomach. So, calcium carbonate, in the form of chalk, is found in many brands of indigestion tablets which are available from chemists and supermarkets. So when you have acid indigestion, you'll swallow one of these tablets and it actually contains calcium carbonate powder, which then reacts with the acid and neutralizes it, because the calcium carbonate itself is a base. So a base, as we said before, is a compound that accepts hydrogen ions when it reacts with an acid. So all bases accept hydrogen ions, which are protons, and so bases can be defined as proton acceptors. So typical bases are things like metal oxides and metal hydroxides. So copper oxide is an example. Alkalis are soluble bases. Now, alkalis are bases which dissolve in water and typically will produce hydroxide ions in solution. Now, like strong acids, all strong alkalis are completely ionized into their oppositely charged ions when you place them in aqueous solution in water. So here we see what happens with sodium hydroxide and also potassium hydroxide, which are two strong alkalis. They're both bases, but they are alkalis because they are water-soluble bases, and they're both strong alkalis because when you place these substances in aqueous solution, almost all of their molecules, their formula units, are completely dissociated into their oppositely charged ions. Now, all weak alkalis, by contrast, are partially ionized in water, and so an example of a weak alkali is ammonium hydroxide. Ammonium hydroxide has, or rather ammonia has the formula NH3, ammonium hydroxide has the formula NH4OH, and so when this dissolves in water, this forms the NH4 plus ion and the OH minus ion. So ammonia solution acts as an alkali because when you dissolve ammonia in aqueous solution, it causes the dissociation of water into H+, which bonds with the NH3 to form NH4+, and OH-, which then goes off into solution. So you formed, by dissolving ammonia in water, you have formed ammonium hydroxide solution, which is composed of positively charged ammonium ions and negatively charged hydroxide ions. Now, water itself is very, very important in determining the properties of acids and alkalis. So if the following substances are tested with universal indicator paper, the results would be as follows. So if we take sodium hydrogen carbonate crystals, we'd find that there was no change. If we test sodium hydrogen carbonate solution by dissolving those crystals in water, we find that the pH is highly alkaline, so 8 or higher. Citric acid crystals, the solid crystals of citric acid, would show again no change, but if we dissolve those same citric acid crystals in water to make a solution, we get a low pH value, an acidic pH value of 2. So the pH of substances only really exist when those substances are dissolved in solutions. So concentrated sulfuric acid is hardly dissociated as little water is present. So when we have concentrated sulfuric acid, there's very little water present, and therefore almost all of the sulfuric acid molecules themselves are in the molecular form and haven't broken apart to form hydrogen ions and sulfate ions. But when we add this to water, the sulfuric acid can dissociate to produce sulfate ions, and the hydrogen ions will then bond, each hydrogen bonding with a water molecule to form a H3O plus or hydroxonium ion. So if we take water molecules and we combine them with concentrated sulfuric acid, we would get a combination of sulfate ions, SO4 2-, and hydroxonium ions, where the hydrogen ion from each sulfuric acid molecule has broken off and combined with the water molecule to form H3O plus, a hydroxonium ion. So this would be the arrangement of particles in a dilute sulfuric acid solution. Now obviously when we're testing for the presence of alkalis and acids, we can use indicators which change colour depending on how acidic or alkaline a solution happens to be. So indicators can be used to demonstrate the presence of both alkalis and acids. Now, two indicators that you should be familiar with are litmus and universal indicator. Litmus has two forms, blue and red. So blue litmus paper and red litmus paper can be used to test the presence of acids, which turn red with blue litmus, and alkalis, which turn blue with red litmus, respectively. Now, litmus has a limited use as it doesn't give an indication of the pH or the strength of an acid or an alkali, but universal indicator is a mixture of several indicators, including litmus, which have been carefully chosen to show a distinct color at different pH values. So universal indicator paper and universal indicator solution are both commonly used in school laboratories to test the acidity or alkalinity of a solution. So here we can see the universal indicator in the presence of a strong acid turning red, and then in different concentrations and different strengths of acid or alkali, we get the characteristic colors, which we can then use a color scale to identify the pH of those solutions. So the acidity of a solution is measured by the concentration of hydrogen ions, which is expressed in terms of pH. So the more hydrogen ions an acid produces when it dissolves in water, the stronger it's described as being and the lower its pH value. Pure water has a pH of 7.0, which is the pH of a neutral solution with equal quantities of hydrogen and hydroxide ions. Now, the pH scale is not an arbitrary one, it is actually a calculated scale. But essentially, the lower the pH number is below 7, or the higher the number it is above 7, these indicate increasing acidity and increasing alkalinity respectively, and 7 is the neutral pH. So if an acid is added to pure water, the hydrogen ion concentration increases, and this causes the solution to become more acidic, which is measured as a lower pH value. Conversely, if we add a soluble base, an alkali, to pure water, the hydrogen ion concentration decreases because the alkali is a base. It bonds with the available hydrogen ions and removes them from solution, and so we end up with a solution which is increasingly alkaline. Okay, everyone, so before we go on to the next topic, we're coming rapidly up to the next 5-minute break here. So many of you asked me to cover, I believe, let me just check the list here. Okay, so yeah, all right. So it seems like most of you asked me to cover titrations. Now, I did actually cover the topic of titrations in the last GCSE Chemistry webinar where we talked about calculations and quantitative chemistry. So if you're after the calculation aspects of titrations, then I would encourage you to go to the webinar resources page for that one and have a look at the interactive video with the questions embedded, the slides, the various resources, and if you have any questions, then go ahead and ask your questions in either the live chat or via the private messaging function on that page. In the context of this particular webinar, I'm going to cover the practical aspects of doing titrations. However, because we've come up towards the next 5-minute break, I'm going to pause here and allow you guys to take a short break. But also, again, you should see a poll pop up on your screen, those of you who are attending, which should allow you to vote as to whether you'd like me to continue for an extra 30 minutes after the break, either on exam questions or continuing with the topic teaching. Again, the next topic which received the highest votes is titrations. Alternatively, you can vote for whether you'd like me to just go straight into the Q&A section. I see that the vast majority of questions asked in the Q&A panels across all 5 student groups here have been about oxides and the properties of oxides. So if you do choose to go into the Q&A segment, I'm going to go and lead with that. But in any case, take a 5-minute break and I will see you in 5 minutes time. Okay everyone, we're back after the 5-minute break, and I see that from the poll numbers it seems like the majority of you have voted for me to continue into the Q&A section, so I will do that. So let's take a look at the questions that you've asked in the Q&A panels for the different student groups, and I'll be answering the questions in the order in which they received votes, so bear with me while I have a look here. All right, so it seems like the question in its various forms which has received the largest number of votes from students in all 5 of the student groups is to talk about oxides and the preparations of the oxides of various materials. So let me find the relevant slides and go into that. All right. So, firstly, let's start with how the oxides of various common elements or common oxides of elements are prepared in the laboratory. So, let's start with this. So, at room temperature, hydrogen peroxide, H2O2 solution, will decompose relatively slowly into water and oxygen. So, this is a viable means of giving off oxygen in gaseous form. Now we can speed up this relatively slow reaction that occurs at room temperature by adding a catalyst, manganese 4 dioxide. When we add this to hydrogen peroxide, the reaction proceeds much more rapidly. And so the manganese 4 dioxide is a catalyst. It will speed up the rate at which oxygen is evolved by this reaction, but because it's not been used up in the reaction, it doesn't appear as a reactant or a product, and it can actually be reused after it's been reclaimed and purified from the reaction mixture. And so, in this sense, the manganese 4 dioxide is acting as an inorganic catalyst for this reaction. So another means by which we can prepare oxygen in the laboratory is by the downward displacement of water. Now, it's all very well allowing hydrogen peroxide to decompose to water and oxygen. However, that you have to have some means of catching that oxygen gas and not allowing it to escape from the reaction vessel. And so the way that we do this in the laboratory is by means of this apparatus here. So again, the reaction that's happening here is that hydrogen peroxide in the presence of the manganese 4 dioxide catalyst is breaking down to produce water and oxygen. The water stays in the liquid at the bottom of this round bottom flask, and the oxygen is comes out of the round bottom flask via this delivery tube and is then caught in an upturned cylinder which has already been filled with water, and the mouth of the cylinder submerged under the water in this tray. So as the oxygen bubbles accumulate, they displace the water in this tube and displace it downwards in this manner. So here's the word equation for this reaction. This is the balance symbol equation. So the formula for hydrogen peroxide is H2O2. We're producing water and oxygen, and so we balance the equation by having 2 moles of hydrogen peroxide to 2 moles of water produced and 1 mole of oxygen produced. So we can measure the rate of this reaction by means of a different set of apparatus using a gas syringe. And so the rate of reaction, the different means of measuring and calculating rates of reaction is something that we're going to go into in a later webinar in this GCSE Chemistry revision series. But for now, it's important to understand that we can also measure the rate at which the oxygen is evolved by means of a gas syringe, where we're measuring the volume of oxygen produced per unit of time. We can then plot the results of that on a graph, and we can see that the catalyst, if we are measuring the reaction in the presence of 3 different catalysts A, B and C, if the rate of the reaction is the volume of gas produced per unit of time, then the fastest rate of reaction is signified by the graph with the steepest slope, with the highest gradient. So we can see here that catalyst C is more effective than catalysts A or B because the slope of the graph, which indicates the volume of gas produced per unit of time, is greater. So we can also prepare carbon dioxide and capture the carbon dioxide again by the downward displacement of water using very similar apparatus, but this time we're using the reaction between an acid and a metal carbonate to liberate carbon dioxide. And so when you react an acid with a metal carbonate such as calcium carbonate, which you find in marble chips for example, the products are always the salt of the metal, in this case calcium chloride, as well as water and also carbon dioxide gas. And so carbon dioxide is an important oxide which needs to be prepared in the laboratory, and if it does need to be prepared in the laboratory in gaseous form, it can be done by means of this apparatus using this reaction. So another method uses the same chemical reaction, but this time we're going to be looking at the upward displacement of air rather than of water. Now, the carbon dioxide has a higher density than atmospheric air, and so if we use the same round bottom flask, and this time the delivery tube delivers the carbon dioxide to the bottom of an upturned gas jar with air inside it, then the carbon dioxide, being more dense than air, will collect at the bottom, and as it builds up it will displace or push the air in the jar out through the hole in the top of the card. So once again we have the same chemical reaction. So in addition to being denser than air, carbon dioxide has several other properties which can be exploited in several different products. So solid carbon dioxide, so-called dry ice, has been added to these test tubes, and carbon dioxide is one of these substances which shows sublimation. In other words, the direct physical change of state from solid to gas or from gas to solid with no liquid phase in between. So excuse me. So, dry ice is commonly used in theatres, for example, where they place the pellets of solid carbon dioxide into, for example, water, and the dry ice will then absorb thermal energy from the water sufficient to cause it to sublime into a vapour, and this then causes that mist which then spills across the stage in theatre productions. So it can also be used to keep ice cream cold, and as I've said, in the theatre it produces this kind of gothic atmosphere using this mist which drifts in a very spooky fashion over the surface of the stage. So carbonated water, which is used in fizzy drinks and also in other products, is made when we dissolve carbon dioxide in water under high pressure. So this carbonated water can then be used to make various products such as colas and other fizzy drinks like these. So the gas inside carbonated drinks is held in solution and prevented from leaving the solution due to the pressure inside the sealed bottle or the can. When the gas pressure is released by opening the bottle or opening the can, the gas then bubbles out of the solution. So carbon dioxide also has an important role in fire extinguishers. So carbon dioxide inhibits normal combustion by excluding oxygen from the region of the fire. So if you have a fire burning on an object on the ground, you can spray the carbon dioxide vapor, the carbon dioxide gas, over the fire. Once again, the carbon dioxide is heavier than the air, it's denser than the air, and so by spraying it over the region which is burning, you are excluding atmospheric air and robbing that fire of oxygen. So CO2 extinguishers or Class B extinguishers should only be used on electrical fires or those involving the combustion of fuels such as petrol or diesel. So, we mentioned before that various metal carbonates, such as copper carbonates, will thermally decompose. That is to say that you take the metal carbonate and you don't react it with some other element or compound. Instead, you simply heat it and it will break down to produce the metal oxide and carbon dioxide gas. So as we saw before, copper carbonate will turn from green to the black colour characteristic of copper oxide, and in so doing it will also give off carbon dioxide, and so this is the balanced symbol equation for that reaction. So zinc carbonate will also decompose when heated to produce zinc oxide and carbon dioxide gas, and this also shows a characteristic colour change. So zinc carbonate will turn from a white colour under heating to a more yellow colour when heated, and so we're going from the zinc carbonate powder to zinc oxide, and again this chemical change happens by breaking off 2 oxygen atoms and 1 carbon atom from this zinc carbonate to form zinc oxide and carbon dioxide gas. So this is this substance, zinc oxide, is referred to as a thermochromic substance, in the sense that when it's allowed to cool, it will change colour back to white. So this is the colour that it appears once straight after the reaction once it's produced at a high temperature, but if you allow it to cool, it will turn back to a white color. So the burning of magnesium and oxygen is a reaction that we've encountered in several contexts during these revision webinars for GCSE chemists. So we have magnesium ribbon, which you commonly find in school laboratories, and when we burn this in a Bunsen flame, it tends to burn with this brilliant white light. What's actually happening is that it is rapidly chemically combining with oxygen in the air to form a white deposit, a white powdery substance, magnesium oxide. And so here's the word equation for the reaction. And as I've said to you before, when you see symbol equations like these, they actually describe the relative numbers and the structures of the interacting particles. So here we're starting with 2 atoms of magnesium in magnesium metal and 1 molecule of oxygen gas, which is composed of 2 oxygen atoms chemically bonded together. So when these reactant particles collide with each other with sufficient energy, the bonding changes to produce 2 formula units of the product, magnesium oxide. Now, we've mentioned before that the alkali metals react readily with oxygen by combustion to form metal oxides, and so the group 1 alkali metals will all react in this way to varying degrees of or with varying degrees of vigorousness due to their varying reactivities. So for example, if we take a lump of sodium and heat it in a Bunsen flame, it will burn with a characteristic orangey red color to form sodium oxide. Now, sodium will also react rather more slowly, but still relatively quickly, with atmospheric oxygen, and so sodium is a soft metal which can be cut with a bread knife. When you cut it, it reveals a shiny surface which rapidly will become dull and tarnished because of its reaction with oxygen molecules in the atmosphere. So sodium oxide, the oxide of this group 1 metal, is a base. When you dissolve it in water, it forms sodium hydroxide solution, which is a strong alkali. Now, a base, again, is a compound that accepts hydrogen ions when it reacts with an acid, and as we saw before, all bases will accept protons or hydrogen ions, and therefore bases can be defined as proton acceptors. Now, metal oxides and hydroxides do behave as bases. Alkalis, once again, are soluble bases, which when they dissolve in water will produce hydroxide ions in solution, and it's these hydroxide ions which will chemically react with hydrogen ions to remove hydrogen ions from the solution. Now, all strong alkalis are completely ionized in water. These ionic substances will dissociate into their separate positively charged metal ions and also hydroxide ions, which are free to move separately in the water. So we see that sodium hydroxide with the formula NaOH will completely dissociate in aqueous solution to form separate unipositive sodium ions and separate uninegative hydroxide ions. In the same way, potassium hydroxide, the hydroxide of another metal in group 1, will do the same thing. Potassium hydroxide has the formula KOH and will dissociate into potassium and hydroxide ions. Now, weak alkalis are distinct from strong alkalis in the sense that they are only partially ionized in water. So again, the example that we saw before is when you dissolve ammonia, which is NH3, in water, you form a solution of ammonium hydroxide containing ammonium ions, NH4+, and OH- ions. The H+, which was added to this NH3 to make NH4+, comes from water molecules, and the OH-, which is left over from that water molecule, becomes the hydroxide ion. So ammonia solution will act as an alkali because it causes the dissociation of water, producing ammonium and hydroxide ions. Now, the oxides of non-metals, such as carbon dioxide and sulfur dioxide, can also dissolve in water, but this time these oxides will dissolve not to form alkalis, but to form acids. Acids, once again, are substances which will release hydrogen ions in solution, and it's these hydrogen ions which make acids proton donors, which give them the characteristic chemical properties that acids have. Now, because all acidic solutions contain ions, they tend to be good electrical conductors, good electrolytes. So once again, when we electrolyze an acid, we produce hydrogen gas at the cathode. And again, all strong acids are completely ionized in water, as we saw before. Now again, weak acids are weakly ionized. In other words, not all or most of the acid molecules will remain in their undissociated states. So again, here are some examples of weak acids here. Okay, so the second most highly rated question in various forms is to talk about salts, the structure and the naming of salts. So let's have a look at that. Bear with me a second and I'll find the relevant slides that I can use. Alright, so let's take a look at salts. So we've already mentioned many reactions which produce salts. So a salt, again, is formed when an acid reacts with a metal or a base, and salts are often familiar chemicals, such as sodium chloride, which is common table salt. But chalk, limestone, and marble are all rocks which contain a high proportion of another salt, calcium carbonate. Salts are ionic compounds and therefore have a number of characteristics which are specific to ionic compounds. Typically, they have high melting and boiling points, and they can be used as electrolytes. They also form regular geometric crystal structures as well, and most of them, not all, but most of them, are water soluble. So, we mentioned that acids react with bases such as metal oxides and metal hydroxides, and one of the products of such a neutralization reaction is a salt. So here we have an animation showing the reaction between this base, copper oxide, and sulfuric acid to produce the salt, copper sulfate, and water. Now you'll notice that the salt is always formed from the positive ion of the metal, which comes from the base or from the alkali, and the conjugate ion, that is to say the ion from the acid, the negatively charged ion, which is not the hydrogen ion, the positively charged ion. So again, so if we show what happens here, we start with copper oxide and sulfuric acid, and the bonds will reorganize themselves during the course of the reaction to form a water molecule and a copper sulfate formula unit. So the bond between the copper ion and the sulfate ion is an ionic bond, in the sense that the copper ion has two positive charges, the sulfate ion has two negative charges, and the two will attract each other. So we see that this is a salt formed from the conjugate ion SO4 of this acid and the positively charged metal ion from this base. So a base can be used to neutralize an acid, and these are called neutralization reactions, and one of the products is always a salt. Acids will react with metals that are above copper in the reactivity series, as we saw, to form salt and hydrogen gas. So, as we saw, neutralizing sulfuric acid with copper oxide will form a salt of copper and sulfate, copper sulfate. If we neutralize sulfuric acid with metallic zinc, as is being shown in the bottom of this conical flask, we will form a salt again. So, metal, when a metal reacts with an acid, it will always form a salt and hydrogen gas. The salt will always be composed of the positively charged metal ions and the negatively charged ions from the acid. And so in this case, the word equation for this particular example of this type of reaction would be zinc reacts with sulfuric acid to form zinc sulfate, the salt, and hydrogen. So the symbol equation for this would be here. So once the reaction stops, in other words, no more hydrogen gas is being produced, the remaining unreacted metal can then be filtered from the reaction solution using filtration and then used to react with more acid. Now, not all metals can be used for this type of reaction because some metals are too reactive, whereas other metals are not reactive enough. The reactivity of the metal depends upon its place in the reactivity series, as we saw before. So, dilute sulfuric acid and zinc will readily react with each other, but if we were to try the same reaction with potassium or sodium, the reaction would be so vigorous that it would be rather dangerous. On the other hand, at the other end of the reactivity series, if we were to try to react dilute sulfuric acid with silver or gold, we would see almost no reaction because these metals are too unreactive. Let me skip past here. Alright, so acids can also be neutralized with carbonates to give a salt, carbon dioxide and water, as we saw before. So this is another one of these general equations that you need to be familiar with and need to be able to recall, because you may be asked to construct either a word equation or a balanced symbol equation given specific information about which metal carbonate you're dealing with and which acid you're dealing with, or you may be asked to construct that equation using information about the salt that you're going to make, and so on. So if we're reacting calcium carbonate with sulfuric acid, again, the salt is going to be made from the positive ion from the metal carbonate, which in this case will be Ca2+, and the conjugate ion of the acid, which in this case would be sulfate, and so the salt is going to be called calcium sulfate. Now, to determine the formula of the salt, you first need to know what the charge is on the metal ion and what the charge is on the conjugate ion from the acid. So sulfate, you simply have to know, is SO4 2-, and calcium, being in the second group of the periodic table, calcium will form a dipositive ion, Ca2+, and so you only need one calcium ion to balance the charge on one sulfate ion, and so the salt will have the formula CaSO4, and this allows us to balance the equation. Now similarly, carbonate, the ion, the negative ion carbonate, has two negative charges, CO3 2-, and so if you didn't know the formula for calcium carbonate and you needed to enter that formula to make a balanced symbol equation, you could use the same logic. Calcium is Ca2+ because it's in group 2. Carbonate, you simply need to know off by heart, is CO3 2-, and so you only need one carbonate ion to balance the charge on one calcium ion, and so the formula is simply CaCO3. So again, in general, a metal carbonate reacts with an acid to form a salt plus carbon dioxide plus water. So once again, in this reaction, once the reaction has stopped, in other words, no more CO2 is being produced, then the insoluble calcium sulfate can then be removed by filtration. We see here that in this case, the salt is not in aqueous solution, it's in the solid state. It is mixed in with the water in the reaction vessel, but it's not dissolved in the water. And so in this case, we can simply filter this product off and drive the remaining water off by evaporation to form the calcium sulfate crystals. So limestone, as I mentioned before, is a form of sedimentary rock which contains a high proportion of calcium carbonate, and it's widely been used, at least historically, if not more in modern times, as a building material. Now, acid rain contains dissolved acids such as sulfuric acid, and as acid rain falls on these limestone buildings, it does cause corrosion because it will react with the calcium carbonate to form the salts, and those salts will then wash away, and this leaves the building corroded in this manner. So, once again, we have a carbonate reacting with an acid to form a salt and carbon dioxide and water. So in this case, we have calcium carbonate reacting with sulfuric acid to form calcium sulfate and carbon dioxide and water. Okay, so an alkali can be used to neutralize an acid, as we said before. So we can represent these types of reactions using ionic equations as well, because both the acid and the alkali, particularly if they're both strong acids and strong alkalis, both of these substances are going to dissociate to form their ions. And again, the salt, which is one of the products, is itself an ionic substance, which is frequently dissolved in the solution of the reaction mixture. So if we have the general equation for neutralization, we can represent this as a symbol equation. Now, there is the concept of spectator ions in these types of equations, and so typically we would represent the equation something like this. And so for the neutralization of sodium hydroxide with hydrochloric acid, we would need to include the metal ion and the conjugate ion of the acid. And so this is not a correct overall equation. This simply is what you need to remember in terms of the general equation. So if you have a specific alkali, you would need to include the metal ion along with the hydroxide ion and the conjugate ion of the acid to write the balanced symbol equation. So sodium chloride is common salt, and it really is quite common. It's been estimated that the oceans contain as much as 50 million billion tons of dissolved solids, and much of this is sodium chloride. So it's been calculated that if the salt in the sea could be extracted and spread evenly over the Earth's land surface, it would form a layer over 150 meters thick. So here we can see a photograph, excuse me, of the Dead Sea, where salt crystallizes as the sea level falls due to evaporation. And you can see just how much salt there is in that water as it crystallizes out due to the water evaporating under the influence of the heat from the sun. So here we have crystals of sea salt, sodium chloride, magnified over 100 times. So we can see the cuboidal shape of many of these crystals, and this reflects the internal arrangement of sodium and chloride ions. Now, we did go over that in quite some detail in the earlier webinar of this chemistry series on structure and bonding. So if you want some more detail on that, I would suggest going back to that webinar and viewing that. So, ammonium nitrate is an example of a salt which is important in the agricultural context. Many inorganic fertilizers are actually salts of nitrates and phosphates. So the way that we produce ammonium nitrate is, once again, ammonia dissolves in water to produce an alkaline solution of ammonium hydroxide, as we saw before. And so this would be the equation to illustrate that happening. Now this alkali can then be neutralized with nitric acid to produce the salt ammonium nitrate. And so again, the balanced symbol equation for this reaction is this. So ammonium nitrate is an important fertilizer because it provides a lot of nitrogen in the form of ammonium ions and also nitrate ions, which soil bacteria can convert in the case of ammonium, and the plants can absorb directly in the case of nitrate. So this is a very good source of nitrogen, which is essential for plants for them to build things like amino acids, to build proteins with, and so on. So another important application of salts is removing hardness from water. Now we're going to be talking about the purification of water again in more detail in a later webinar of this series, but this context does require us to mention it, at least in passing. Now temporary hardness can be caused by calcium hydrogen carbonate, and this can be reduced by using slaked lime. So this process was developed by Thomas Clark in 1841. Slaked lime, which is calcium hydroxide, is added to the hard water supply. This then converts the hydrogen carbonate into carbonate, which forms an insoluble solid, a precipitate, which can then be removed by simple filtration. So here is the word equation for this process, and here is the balanced symbol equation for this process. So permanent hardness, on the other hand, is caused by calcium sulfate or magnesium sulfate in the water. Now this can be reduced by the addition of sodium carbonate, which is commonly referred to as soda crystals. So the calcium ions from calcium carbonate, which is insoluble, or the calcium ions form calcium carbonate, which is an insoluble solid, and again will form a precipitate, an insoluble product, which can then again be removed by filtration. So this process is described by this word equation here, and we can write a balanced symbol equation to describe this process like this. So soda crystals, also known as washing soda, can be added to the load of a washing machine, and this is typically done to make the water softer or to remove hardness in this way. So to meet environmental standards, all effluents that come from factories must be treated before being released to remove metal ions from those effluents. So in most cases, metal ions can be removed by treatment with sodium carbonate because this reacts with other metal ions to form insoluble carbonates, which can then be filtered and removed from the effluent as a sludge. So a salt is always formed when an acid reacts with a base or a metal. Again, we've seen many of these are rather common substances. Now, the chemical name of the salts produced depends on the acid used. So, nitric acid produces nitrate salts, hydrochloric acid produces chloride salts, sulfuric acid produces sulfate salts, and the other part of the salt name, the first part, the prefix, is the metal which is found in the base or the alkali. So, I hope that answers your question. All right, so I see that we've reached the end of the 30-minute period. So there's a few more questions to be answered. So apologies that we didn't get time to answer those questions, but in large parts, I see that the majority of you have had your questions answered. If you do have any further questions, then please do go to the private resources page and ask your questions either in the live chat there, and I'll be happy to answer them. Or if you prefer to send me a private message, you can log in and go to the private webinar resources page and send me a private message. Okay, everyone, I hope that was helpful, and I will see you in the next one. Take care.